You've tried to understand how FlashAttention actually works, right? It is already running underneath your code whether you asked for it or not. Open PyTorch's own documentation for its attention function, and FlashAttention is the first backend on the list. So you go looking for it, and you find this post from May of 2022 by Dao, back when he was a PhD student at Stanford. No launch event, no press coverage, just this. Now read the claim itself. It says 2 to 4 times faster and 5 to 20 times less memory. And there is one more phrase in there, doing more work than the 2 numbers before it. No approximation. It is the exact same function as ordinary attention, and it returns the same values which match to 6 decimal places. Same inputs go in, the same answer comes out, and only the root between them differs. So how does it actually work? You open the paper, and within minutes you hit a wall. The wall says input, output awareness, tiling, online softmax, and 2 kinds of graphics chip memory. You probably closed the tab and filed it under things only kernel engineers understand. The secret is that you are not bad at this. Nobody has shown it to you the right way around. FlashAttention is the same attention you already know. The only thing that changes is the order the work happens in. The whole thing is built on 2 ideas you already use in daily life. Here's the first one. When a job is too big for the space you have, you cut it into pieces and do one piece at a time. The whole thing never fits, so it never gets laid out whole. One piece is worked on, finished, and cleared away before the next arrives. That is tiling, and it is why the giant table of scores never has to exist. Here's the second one. A cashier watches your groceries go past one at a time and always knows the total without ever writing a single item down. Items arrive one at a time, and each one is added and then dropped. Only one number is ever held, no matter how long the belt is. That is a running sum, and it is how each row keeps its answer while the pieces stream past. Once those 2 click, the hard part of FlashAttention stops being hard. A third trick sits on top of them, and it only makes sense once these 2 are in place. Give me 30 minutes, and FlashAttention will click forever. Here is the whole thing in 28 lines of Python. You are not meant to read it yet. Just notice the shape and pause here if you want a closer look. A function takes the query, the keys, and the values, plus a tile size. The tile size says how many keys get handled in one piece, and it is the only knob the caller sets. It sets up 3 running quantities, a running max, a running sum, and an accumulator. Those 3 are the only per row memory this function ever keeps. It streams through the keys and values 1 tile at a time, and scores each tile against the query. Then 5 lines update the running quantities with each tile. Those 5 lines are the heart of the method, and they are where this video spends most of its time. And at the very end, one division hands back the answer, row by row. Right now, that is a wall of symbols, and everybody's first reaction to it is the right one. We build it 1 line at a time, on a toy example with 4 numbers you can check in your head, and nothing gets skipped. Here's that same code again, next to what you will be able to do with it by the end of this video. You will read every line of it. You will run it against PyTorch's own attention and watch it match to 6 decimal places. And you will say exactly why it is faster without doing less math. 2 quick questions before we start. You are not supposed to know these yet, and we ask them again at the end, when they should feel obvious. FlashAttention is several times faster on the same inputs. What does it change to get that speed? Does it approximate the softmax? Does it drop the low scoring keys, or does it do the same math in a different order? The answer is C. Other tricks pick A or B. They soften the softmax or throw away keys that score low, and they buy speed by doing less work and accepting a slightly different answer. FlashAttention refuses that deal, so the only thing left to change is the order of the work. Changing the order sounds like it should buy you nothing at all, and that puzzle is what we solve next. What changes is when and where each piece of the work happens. Second question, where does ordinary attention spend most of its time on a GPU, the graphics chip that does the heavy math? Computing the scores? Hauling a giant table of scores in and out of slow memory? Or the softmax divide? The answer is B, hauling that giant table through slow memory. A GPU is wildly unbalanced. Its arithmetic is enormously faster than its memory, so multiplying numbers is nearly free while fetching them is not, and dividing is one cheap operation per entry. Ordinary attention scores every word against every other word, and on a long input that is a table with millions of entries. It writes that whole table out to slow memory and reads it straight back, just to hand it to the next step. The chip spends its time waiting on that round trip. To see why that round trip exists, we need three pieces: ordinary attention, tiling, and running sums. Here are the three concepts you need. If you can read basic Python and high school algebra, you have everything this video assumes. The rest is built here from scratch. Attention, the ordinary algorithm that FlashAttention reschedules. Tiling, cutting a calculation into chunks and doing one chunk at a time. And running sums, summarizing a stream of numbers without storing it. Each gets a problem and an answer on the same tiny example. Those three concepts plus one new trick make up the whole algorithm. First, attention, the thing FlashAttention reschedules. Here's the formula. It's 3 parts marked. Q is the thing doing the looking, K is what each entry offers to be matched on, and V is what it hands back. A score, a budget, and a mix. The letter D is how many numbers each key carries, and dividing by root D keeps the scores a sane size. The whole formula is built from scratch in my transformer video, and there is a link on screen and in the description. Here is that same formula as code. It has 3 lines, and each line is one of the 3 parts. Line 1 scores every query against every key. Line 2 normalizes each query's scores into probabilities. And line 3 mixes the values, weighted by those probabilities. Every line is one move of the machine we are about to rebuild. That is all of ordinary attention. Now, we rescheduled it. Here is the quick intuition behind those 3 letters. Think of it as a trip to the library. Your query is the search phrase you walk in with. Each key is a book's catalog label, what the book offers to be matched on. And each value is what that book actually contains, what you would carry home if you picked it. You never pick just one book. You score every label against your phrase, you split one budget of attention across the labels by how well they matched, and you carry home a blend of their contents. You score, you budget, and you mix. To make this concrete, we use the smallest example that still has every piece in it. 1 query, 4 keys, and 1 value behind each key. These are the only numbers in our running toy example, so let's name them. Q equals 1 is the query. It is the one thing doing the looking. K equals 2, 1, 3, 0 are the 4 keys, 1 per book. The score each key gets is how well it matches the query. And V equals 10, 20, 30, 40 are the 4 values, 1 behind each key. The values are spread far apart on purpose, so a wrong mix is obvious at a glance. Step 1. Score. Score every key against the query. The amber step boxes hold the 4 multiplications. Our query is a single one, so each score comes out equal to its own key. That is the point of picking one. The scoring step is real, but it stays out of the way of the arithmetic that matters. Step 2. Softmax. This step turns 4 scores into 4 shares of 1 budget, and it is the step that will cause all the trouble. Here is its formula. The formula makes 2 moves, it raises E to every score, and then it divides each result by Z, the total of all of them. We take the 2 moves one at a time. First, raise E to each score. A score of 3 was only 1 point above a score of 2. But E to the 3 is nearly 3 times up to the 2. That gap makes the biggest score dominate everything downstream. Then add them all up and divide. Watch the arrows converge on the 1 red box. Add the 4 exponentials and you get Z, 31.1929. Book 1 contributed 7.3891, and 7.3891 divided by 31.1929 is 0.2369, its share. Now follow the arrows because the shape is the whole problem. Every exponential goes into that one shared total, and the total comes back out to every share. No share can finish until all 4 scores have arrived. Look at the shape of that budget to see what softmax is really doing. Look at the tall green bar. 64% of the whole budget goes to the single best key. The scores only span 0 to 3, but the shares span 3% to 64%. So an extra point of score multiplies the share by about 2.7. The largest score dominates the answer, and it is the one number we will have to keep watching. Step 3. Mix. Each share multiplies the value sitting under it, and the 4 results add up. Here's the mix again. Each share times its value, with the results read along the bottom row. Book 3 matched best. It took 64% of the budget and dragged the output up toward its own value of 30. Add the 4 results and you get 24.7115. 24.7115. We chase this number for the rest of the video. The key idea. Attention is score, then budget, then mix. FlashAttention keeps this exact computation. It changes only when and where each part of the computation runs. One convention for the whole video. We show rounded numbers and every result comes from a real run at full precision. The 4-digit shares make the total look like 24.712, and the code prints 24.7115. We won't flag this rounding again. Second concept, tiling, and first, why we need it at all. Our example fits on a slide. A long context model does not, so let's put the gap in numbers. Our toy has 1 query, 4 keys, and 4 values. An illustrative long context model reads 8,192 tokens at once, so it has that many of each. Each key carries 64 numbers. That width is called the head dimension, and a head is one independent copy of this whole attention calculation. Scores to compute, every query against every key. That squares the sequence length, and 8,000 keys become 67 million scores. At 2 bytes each, that is 128 megabytes to hold them. And that is one head. A model runs 32 of those copies at once, which is 4 gigabytes. Reading down those last rows is the whole problem. 8,000 keys become 67 million scores. 128 megabytes for a single head. You might think 4 gigabytes does not sound alarming. An A100 has 80 gigabytes of memory on it. So why is any of this a problem? The problem is not space. The problem is distance. The score table needs 4 gigabytes, and the card holds 80. But the fast tier holds 20 megabytes because the card's memory is not one thing, and the fast part of it is very small. And every number in the table makes that commute twice. Think of a busy kitchen. Every cook has their own small station, and across the room is one big shared storeroom, holding everything the restaurant owns. Reaching for something on your own station costs nothing, and every cook can do it at the same time. Walking to the storeroom is different. It is far, and everyone shares it. A cook who walks back there for every single ingredient spends the shift walking instead of cooking. A GPU is laid out the same way. The stations are SRAM, static RAM, the small fast kind. The storeroom is HBM, high bandwidth memory. Both are in the same kitchen, but only one of the two is in arm's reach. Here is the shape of a GPU, stripped down to the part that matters. Inside that GPU, there are 2 places to keep numbers. SRAM sits on the chip next to the compute units. It is fast, about 19 terabytes per second, and it is tiny, about 20 megabytes. HBM is the number printed on the box, 40 or 80 gigabytes, and it is more than 10 times slower to read from. The 128 megabyte score table cannot stay in SRAM. It gets written down to HBM and read back up again, and the compute units sit idle while the table travels. And those are not our numbers. They are the paper's own, from Figure 1 of FlashAttention. SRAM at 19 terabytes per second and 20 megabytes. HBM at 1.5 terabytes per second and 40 gigabytes. Arithmetic is nearly free. Moving numbers is what costs. So we break one calculation that does not fit into a sequence of smaller ones that do. Each chunk lives on the fast tier, gets used, and is thrown away. That is tiling, and it is the sheet and the desk from the opening. The desk is SRAM. The sheet is the score table. Nothing about the job changed. We only changed how much of it is on the desk at once. Now, the problem, on the same friendly example from before, with one thing taken away. We keep the same query, the same keys, and the same values, and we still want 24.7115. But now there are 2 workers, and each worker can only hold 2 of the keys along with their values. In the real kernel, one worker streams the tiles one after another, and the parallel win comes from many query rows. 2 side-by-side workers are simply the clearest way to see what has to combine. Worker 1 gets the first 2 keys. Worker 2 gets the last 2. Neither worker ever sees the whole row. Can they still land on the same answer? Neither worker ever sees all 4 keys, and the answer must still be 24.7115. Part 1 of the answer, the scoring splits perfectly. Both workers take the same query and multiply it against the keys they happen to hold. From there, they are on their own. Worker 1 never needs to know what key 3 scored, and worker 2 never needs to know about key 2. They can run at the same moment, on different parts of the chip or different chips entirely, and both finish without waiting. Everything is parallel until the softmax calls a meeting. Then the softmax arrives and both of them stop. To turn any of those scores into a share, you need Z, and that Z is the total overall 4. Worker 1 cannot compute it because 2 of the 4 numbers are sitting on the other side. Worker 2 cannot compute it either. Both have to stop, hand over what they have, and wait for the answer to come back. That is what it means when people say the softmax does not parallelize. The softmax is not slow. It forces a meeting point in the middle of the calculation. A meeting point is exactly what tiling was supposed to remove, and removing it is the rest of this video. The mix at the end cuts the same way, because addition does not care what order you do it in. Tile 1's piece comes to 4.111, tile 2's to 20.601, and they add back to the same answer. Here's that same split drawn out with only one running total ever in memory. Scoring and mixing different tiles are independent jobs, so they can run on any schedule without changing the answer. The key idea: scoring and mixing split cleanly across tiles, because each tile minds its own business. The softmax does not. Its denominator reaches across the whole row, and that one shared total is the entire problem this video solves. Third concept. So how do we unblock the softmax? Here's where we stopped. Everything is jammed on that one red box, which holds the total of all 4 exponentials. We are not allowed to hold the whole row, and we need to arrive at that total anyway, so we must build it out of pieces that show up a few at a time and get thrown away. Strip the attention off, and it is plain arithmetic. Numbers arrive, each batch is discarded before the next one shows up. How do you still end up knowing their total? The way out is one you already use. It is the checkout from the opening. The cashier never holds the list. They hold one number, add each item as it goes past, and let the item disappear into the bag. That is a running sum, and the same one-number trick carries to a running max. Attention needs both, one for the total and one for the biggest score so far. It does give something up. It is not parallel at all. Each step needs the answer from the step before it, but the memory it needs never grows. Here is the problem one more time, written out. The row of 4 scores is cut into 2 tiles, and each worker holds exactly one of them. The quantity the softmax needs is the sum over the whole row, all 4 exponentials in one total. Worker 1 can do its half, and worker 2 can do its half. Neither may hold all 4 terms at once, because holding the whole row is the thing tiling exists to avoid. Can we produce Z seeing one tile at a time, and discard each tile before the next arrives? Here's that question in code you can run. The row arrives 2 scores at a time. A running sum is the only thing we keep. Each score is added to the running sum and then dropped. After tile 1, 10.1073. After tile 2, 31.1929. Exactly the Z we needed. Here is what that loop just did, drawn out. Read along the bottom row. The running sum starts at 0, tile 1 lifts it to 10.1073, and tile 2 carries it to 31.1929. Each tile is used the moment it lands and gone by the time the next one shows up. The 2 amber groups above are never on screen together. The whole row was never held, and Z came out anyway. The key idea: a running sum turns a quantity that needs the whole list into one number you carry along an update. It costs you parallelism inside a row, but the memory it needs never grows. Pop quiz. You cut a score row into 2 tiles. 2 of these can be worked out on each tile separately and then combined afterwards. Which one cannot? A running sum, a running max, or a softmax weight? The answer is C. A running sum combines by adding. A running max combines by taking the max of the 2 maxes. Both fold together with no trouble. A softmax weight is the odd one out, because each weight divides by a total over the whole row, so no simple combine works. That single fact is why the obvious approach breaks, and the whole next chapter builds the fix. Those are the 3 concepts. Now we put ordinary attention and FlashAttention side by side, because the difference is smaller than you would think. Here is ordinary attention again. 3 lines, and the whole score table exists in memory on the first one. And here's FlashAttention, the whole function from the opening, with every line labeled by the concept it came from. The three running quantities are concept 3, a running max, and 2 running sums. The loop over chunks is concept 2, tiling. The scoring inside the loop is concept 1, attention on this tile only. The updates fold each tile into the running quantities. And one line has no label because nothing explains it yet. Same 3 moves, score, softmax, mix, with 2 simplifications so the code stays readable. 1 attention head instead of many, and all the queries held in memory at once. Neither touches the logic, and every move now happens on a tile, with the running values carrying the answer across the gaps. One line has no label yet. That line is the whole hard part. We are going to work through this algorithm block by block and line by line. We will do this until every part is something you could have written yourself. We are done with the background. Scores, softmax, tiling, and running sums, all on our same 4 numbers. So now we can look at the hard part. Here is the full function from the beginning again, with the lines we still need to explain marked, and you will understand all of them in a few minutes. Those 5 marked lines track a maximum. Measure every exponential against it, and multiply both totals by old scale before adding anything. That sounds like a lot of moving parts just to keep a running sum, so we are going to look at why we need it. The full problem. The query is 1 and the 4 keys are split across 2 workers. Worker 1 holds 2 and 1, and worker 2 holds 3 and 0. We want the softmax. Each key takes its own exponential e to the s and divides it by z, the total of all of them. And one constraint is the whole difficulty. Neither worker may ever hold all 4 scores at once. We did find a way to get a total without holding everything, so here's a plain running sum over the tiles and it works just fine. 4 lines of loop and 1 held number. And it lands on exactly the z the workers were stuck on. 4 lines, problem solved. So why are we still talking about this? Because we ignored a detail. Attention scores are not guaranteed to stay small. And e raised to a large number overflows to infinity. And remember how fast the exponentials grew on our own 4 scores. A 3 only beat a 2 by 1 point, but e to the 3 nearly tripled e to the 2. 1 extra point of score multiplies the entry by about 2.7. This limit comes from the number formats themselves, because each number format can only store values up to a fixed limit, and e to the x exceeds that limit quickly. In FP32, floating point 32, e to the x overflows once x passes 88.7. BF16, brain floating point 16 has the same limit, 88.7, but FP16 tops out at 65,504. So e to the x overflows once x passes 11.09. Real training runs in FP16 for speed, and past 11 the exponential is already infinity. No real implementation gambles on scores staying small. Past a score of 11, e to the x is already infinity. The fix uses a simple trick. You can subtract any constant c from every score and the softmax does not change, because e to the minus c appears in the numerator and the denominator and cancels out. We pick c equals m, the biggest score in the row, which makes every exponent 0 or negative. Here is the whole calculation on the 2 scores from the burning screen, both ways. Score 1000. Naively, e to the 1000 is infinity. Shifted, e to the 0 is 1. Score 999. Naively, infinity again. Shifted, e to the minus 1, 0.3679. The totals row is where they part. The naive total is already infinity, while the shifted total adds to 1.3679. So the naive shares are infinity over infinity, which is nan, not a number, while the shifted shares come out 0.7311 and 0.2689. In the shifted column, every exponent is 0 or negative, so every entry lands between 0 and 1, and nothing can overflow. Here is the same walkthrough as code you can run. The naive line first. Then subtract the max before exponentiating. Naive prints none, shifted prints the real shares. Every real implementation subtracts the row maximum to avoid overflow, and ours does too. Shift by the maximum and nothing can overflow. That leaves one last problem, because streaming one tile at a time means each worker can only shift by the biggest score it has seen. Worker 1 shifts by its own maximum of 2, so its entries are 1 and 0.3679, and they sum to 1.3679. Worker 2 shifts by 3 and its entries sum to 1.0498. Each sum is correct for its own tile, but the 2 are measured against different maximums. The red box asks, how do these combine? They combine with one multiplication because exponentials let a shift be swapped after the fact. For any score s and any two reference points p and m, e to the s minus m equals e to the s minus p times e to the p minus m. The factor e to the p minus m has no s in it, so it is the same for every entry, and a whole sum measured against p moves into units of m with 1 multiply. Worker 1's sum moves into units of 3 with EE to the 2 minus 3, which is 0.3679. 0.3679 times 1.3679 is 0.5032. Apply that to the picture, and the question mark resolves. 0.5032 plus 1.0498 is 1.5530. And that is exactly what the whole row gives at once, because shifting all four scores by the true maximum of 3 and summing lands on the same 1.5530. Two workers, one multiply, and the denominator comes out identical, digit for digit. Go back to the attention formula, because we are one factor away from done. The score is done, the budget was just reconciled, the mix is still missing. Here are the givens one more time, so every number on screen has a home. The query is 1. The keys are 2, 1, 3, 0, and since the query is 1, those are also the scores. The values are 10, 20, 30, 40. The row maximum is 3, and the shifted entries are 0.3679, 0.13531, and 0.0498. Now we give the two sums their names and their full formulas. The plain sum of shifted entries is the letter L, and it comes to 1.5530. The same entries times their values is U. 0.3679 times 10 plus 0.1353 times 20 plus 1 times 30 plus 0.049. 8 times 40 comes to 38.3770. Every share divides by the same L, so the division moves outside the sum and happens once. The output, O, is U divided by L, the weighted total over the plain total. 38.3770 divided by 1.5530 is 24.7115. The division happens once, at the very end. ANTA splits across the two workers exactly like L did with the same conversion. The amber entries are exactly the ones from the last two pictures, untouched, and the values sit under them in their own boxes. For each worker, multiply every entry by its value and add the results. Worker 1's total is 17.3576, and Worker 2's is 31.9915. From there, it is the same moves. Convert Worker 1's sum with the same 0.3679, add Worker 2's, and divide the green 38.3770 by the 1.5530 we already have. The fastest way to see all of it is the code. This is the whole reconciliation, with both sums included. Each worker builds its shifted entries and two sums from them. The letter L is the plain sum, and U is the same entries with values attached. Worker 1's come out 1.3679 and 17.3576. Worker 2's come out 1.049, 8 and 31.9915. One alpha converts both of Worker 1's sums at once. Worker 2's add at face value. And a single division at the end. 24.7115, the exact answer ordinary attention gives. With two workers, we merged once. The real loop keeps going, so let's see its shape before we read it as code. Here is that shape drawn as a chain. Each tile folds into one running state, and the amber lines at the bottom are the whole fold. Take the bigger maximum, convert the old totals, then add the arriving tile's own sums. Every fold needs the state before it, so the loop over the tiles is a chain, strictly in order. The parallel win comes from somewhere else entirely. Every query row runs its own chain independently, which is how the real kernel gets its parallel work back. Now the full function from the top of this section, because every line of it is readable. Watch the 5 update lines up close. New max, old scale, tile weights, and the two converted sums. New max is the bigger of the maximum so far, and this tile's own maximum. Old scale is the conversion factor from the old units to the new. When the maximum does not move, it is e to the 0, which is 1, and changes nothing. Tile weights are this tile's shifted entries, measured against the new maximum. Running sum is L. Convert what we have, then add this tile's sum. The accumulator is U, the same conversion, then this tile's weighted sum. And the return line is one division, at the very end. Old scale is the conversion from the pictures, and that was the last unexplained line in the function. Every line of FlashAttention is now readable. Pop quiz. Worker 1's maximum is 2 and worker 2's is 3. To move worker 1's totals into worker 2's units, what do you multiply by? E to the 1, e to the minus 1, or e to the 0? The answer is B. The factor is e to the 2 minus 3, which is e to the minus 1, about 0.3679. Because 0.3679 is smaller than 1, it scales worker 1's totals down, so they sit in the same units as worker 2's. Getting the sign backwards would blow them up instead. And e to the 0 is what you get when the maximum does not move at all, which is the one case where no conversion is needed. One more. The conversion multiplies both L and U. Why both? GPU speed? Because both are built from entries measured against the same maximum, or because the values shrink? The answer is B. Every entry inside ELL and every entry inside U carries the same shifted factor. So, when the maximum changes, both totals are in the wrong units together, and both need the same single multiply. It has nothing to do with speed, and the values themselves never change. Only the weights they are multiplied by do. That is the whole forward pass. A production kernel adds 3 more things, and none of them changes the math. Many query rows at once. Every row runs the same loop with its own maximum and its own totals, and rows never touch. That is why our state was shaped NQ by 1 all along. The causal mask. Future words scores are set to minus infinity before the max, so the model cannot peek ahead. And fusion. The whole loop is compiled into one GPU launch instead of one memory round trip per line. None of those change the answer. This is the moment the opening promised. We run our finished loop against scaled.productAttention, the official PyTorch function from the very first slide. The PyTorch team wrote it, we did not, so agreeing with it actually means something. We run it on the toy and then on a random shape. Here it runs PyTorch's plain reference version, and our loop has to land on the exact same numbers. The toy prints 24.7115, and the biggest difference against PyTorch is about 1 part in 10 million. Between two independently written implementations, the gap that remains is just floating point addition done in a different order. That is the promise paid. You can read every line, and it matches PyTorch. And now the 2 questions from the very beginning, which should feel different this time. FlashAttention is several times faster on the same inputs. What does it change to get that speed? Approximate the softmax? Drop the low-scoring keys, or the same math in a different order? The answer is C, and now you know exactly what the different order is. Every key still gets scored, and every score still goes through the softmax. You watched it match PyTorch a moment ago. Same math, different order, and the table of scores never has to exist. And the second one. Where does ordinary attention spend most of its time on a GPU? The scores, the hauling, or the divide? The answer is B, and you have now counted it. 128 megabytes per head at 8,000 keys, written out to slow memory and read straight back. The arithmetic units wait on that haul, and that is the cost this schedule deletes. You will almost never write this loop yourself. In PyTorch, the whole thing is one call. On a GPU with supported shapes, that one line hands the work to a real FlashAttention kernel, a small program that runs right on the graphics chip. PyTorch picks the backend automatically, based on the hardware, the data type, and the shapes. And this is the same documentation page this video opened on. And now, when PyTorch makes that call, you can trace the tiles, the running maximum, and the one final division that produce exactly the answer you would get the slow way. Now, FlashAttention clicks.